Now let's move on to Grignards. Okay. So with Grignards, the first reaction we want to go over is the acid-base reaction, and I just want to remind you that Grignards will act as a base before a nucleophile, okay? And we'll see what that means in a bit. So let's say we give a carboxylic acid to our Grignard, which is MgCl. Under this condition, the MgCl will simply deprotonate this alcohol and become OMgCl, okay? And the carbon structure that the Grignard was on will be protonated. Okay, so you get both of those products. However, if there are no acidic protons on your carbonyl, we can react this with an organolithium. And so essentially, your organolithium is going to attack that carbonyl and create an alcohol. So we get something like this. So the carbonyl oxygen becomes an alcohol, and we are going to add that carbon structure that was on our organolithium. Okay. And so another type of Grignard attack would be Grignard addition to CO2. And so in this case, our Grignard is going to attack the carbon on CO2. And as a result, we get a carboxylic acid. Okay. And so we're going to see other Grignard reactions throughout, but these are the main core of Grignard reactions, and we'll see other variations on it soon. Now let's go to carboxylic acids. So with carboxylic acids, right, we have, the first thing is the reduction of a carboxylic acid. So with reductions, we're essentially taking those, the carbonyl and all the oxygens, and we're going to replace them with hydrogens, okay? And so that is a reduction. And so in this case, with lithium aluminum hydride, you're going to turn this carboxylic acid into a primary alcohol, okay? And so the main thing here, remember, is that you're taking this carbonyl and you're essentially adding two hydrogens to it. To contrast that, we can also maintain our carbonyl by reducing a carboxylic acid. And in this case, we would use a single reduction of carboxylic acids. So we would go from our carboxylic acid, we would use SOCl2. And if you remember from a few minutes earlier, we're going to take our alcohol and replace it with chlorine. From here, we can use diol H or LTBH. And from here, we will add only one hydrogen to replace that chlorine. Okay. So whereas in this reaction, we added two, this one, we add one hydrogen. Now let's look at Fischer esterification. So Fischer esterification is essentially we're taking a carboxylic acid and we're going to add an alcohol onto it to make an ester. So in this case, our alcohol species is this one right here with the phenyl group. And so we're going to first draw out our carboxylic acid. Okay, and then we're going to replace that OH with the alcohol. And so we get a product such as this. Okay, so we essentially attach that alcohol onto our carboxylic acid to form the ester. And we get H2O as a byproduct. Okay. Next, we have acyl chloride synthesis. And so we saw this in the single reduction of carboxylic acids. And basically, we're taking our carboxylic acid and we're going to replace that OH with a chlorine. So we're just going to chlorinate it. All right. Let's do the next section, which will be esters. So esters are pretty similar to carboxylic acids, and so let's go over them. The first reaction would be Grignard addition to esters. And so with Grignard addition to esters, this is a special case of Grignard addition where we are going to take that carbonyl, sorry, my bad. We're going to take that carbonyl and we're going to replace it with an alcohol as we did with previous carbonyls and Grignards. But in this case, instead of adding our carbon backbone of the Grignard once, we're going to add this twice, okay? And that's because the ester portion of your ester, or the alcohol, the oxygen portion of your ester is a good leaving group, and so I recommend that you try the mechanism out. This should be on the practice midterm 2, I believe, okay? And then we also have reduction of esters. This is the complete reduction. So lithium aluminum hydride, remember, this is a strong reducing agent. So we're going to completely reduce this molecule, and we're going to go from an ester to a primary alcohol. Okay. Then we also have the single reduction of esters, where we're just going to only add one proton. And so in this case, we maintain our carbonyl, but instead of this oxygen portion, we're just going to add one hydrogen to it. And then the last reaction for esters would be ester hydrolysis. And so in this case, we go from the ester, and then upon doing H2O, THF, and HCl, we are going to get our carboxylic acid. And this is the complete reverse of Fischer esterification. Just remember that. Okay. And then this oxygen portion will come off as an alcohol. All right, let's go to dienes. Okay, so for dienes, the first reaction we have is diene halogenation. And so there are two versions of this. So there's the thermodynamic control. And so the way I learned this is that with thermo, you think of heat. And so under 40 degrees, that's like heated conditions, okay? And so we're going to get the thermodynamic product. And so with thermodynamic product, I advise you to review this. But essentially, you're going to get the more substituted alkene, because this is the more stable end product for a thermodynamic control. Whereas for kinetic control, we're going to add the chlorine right here on the diene. And this is less stable because the alkene is monosubstituted, whereas this alkene right here is disubstituted. But the kinetic control happens because the transition state is more stable, which I advise, again, to look through your notes to review that. Now let's go over Diels-Alder. So Diels-Alder, this is essentially you're creating a cyclohexene, and so this involves a diene, and this also involves a dienophile. Okay, and so what we're doing is we're going to combine the diene and the dienophile, and we create a cyclohexene. Okay. Like so. And so that should end the reactions for dienes. Now let's do acyl chlorides. And so with acyl chlorides, this is a very generalized reaction, okay? And so we're going from an acyl chloride. So just to remind you, the acyl group is this portion, which is a carbonyl with a chlorine attached to it, and then any R group could be attached to that carbonyl halide functional group, okay? And so we're going to take any nucleophile in addition to pyridine, and we're going to take that nucleophile and replace the chlorine. So the nucleophile will attack the carbonyl, and chlorine will leave, resulting in our nucleophile being added to the carbonyl. And so this is a general reaction, and so the main difficulty would just be identifying what your nucleophile is. Okay. Now let's move on to nitriles. So there are three main reactions for nitriles. The first one would be organometallic addition to nitriles. And so in this case, we're going to take our organolithium and we're going to add, so let's first draw this, the first part of the structure. So we have the carbon from our nitrile, and we're going to turn that triple bond N into a carbonyl, and we're going to take whatever is added to our organolithium, which is in this case is a phenyl, and we add that to the carbon, okay? And essentially, this is because, remember that organolithiums, the carbon structure that's attached to it becomes a good nucleophile, and so our phenyl would attack that carbon right there, and that's how we add it. And the water and the HCl will create the carbonyl. Next, we have nitrile hydrolysis. So with nitrile hydrolysis, right, we are going to first treat it with HCl and H2O. Our first treatment will end up like so. Okay. So we're going to have a double bonded NH, okay? And the first water is going to attack that carbon, and we get an alcohol. Then, upon treating this molecule with another equivalent of HCl and H2O, the water is going to attack that nitrogen again, and the result, we end up with a carboxylic acid. So we replace the NH, the double bonded N, with a double bonded oxygen. Okay. Moving on to reduction of nitriles. So if you remember, with reduction, we're adding on hydrogens. Okay. And so in this case, we will go from our nitrogen species to a double bonded O, and we're going to add a hydrogen onto there. Okay. And so this is, we're creating an aldehyde.